Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over how to find the slope of a tangent line. This is the second tutorial on our Introduction to Derivative series. Do not forget to visit our website at math.serve.com for access to a wide variety of math tutorials ranging from algebra to calculus. All right, so the instructions for the problem we're working on today are as follows. We are to first of all, find the slope of the tangent line of the given function at a given point using two methods. The first method is the limit definition of a derivative, and the second method is by using differentiation rules. And then the second thing we're to do is to write the equation of the tangent line, obviously making use of the slope from part 1. And then the third thing we have to do is to plot a graph of the situation using a graphing calculator, and then sketch and label the graph on our paper. Lastly, we have to write down everything we can deduce from the results using the tools of calculus, okay? So let's go ahead and get started. The problem or the function under consideration, problem number 1, is f of x equals y cosine x at x equals pi over 2. All right, so let's go ahead and start. We need to find the slope of the tangent line at x equals pi over 2. Okay, so what does that mean? What does the slope of the tangent line at x equals pi over 2 mean? So slope of tangent line at x equals pi over 2 is basically m, right? It's the same thing as m at x equals pi over 2. This is, in calculus terms, the derivative f prime of the derivative at pi over 2, the derivative of the function at pi over 2. Okay? So how do we find the derivative of the function at pi over 2? Well, we are going to have to use two steps. Okay, let's go ahead and list what the steps are. So let's write this down, steps. Step number 1, you are to find the derivative, find f prime of x. All right, and then step 2, you're to find the value of the derivative at a specific value. In this case, we're setting x to pi over 2. So what is the derivative at pi over 2? That will tell us what the slope of the tangent line is. All right. So we're going to carry out these two steps using two methods. Method A is to use the limit definition of the derivative, and then method 2 will be to find to carry out the same procedure using the differentiation rules, okay, the formulas that we already know. Okay, all right, so we want to find the slope of the tangent line. This is part I. So we're going to start with the first method, A. Method 1. Method 1 involves the limit definition. Limit definition of derivatives. That's what we're going to use. All right, this is a little bit longer. Okay, so what is the limit definition of the derivative of a function at a point? Let's go ahead and write down, well, what that is. So the derivative of a function at a point, f prime of x, using the limit definition, is the limit as h approaches 0 of f of x plus h minus f of x over h. Okay? All right, we're going to apply this formula to our problem, our function. So remember there are two steps, okay? So step number 1, we're to find f prime of x, and then step 2, we have to find f prime of pi over 2. Okay, so let's do the first part, which is to find f prime of x. Okay, so let's see, using the limit definition, our function, original function, is 2 cosine x. Okay, now that's this portion of our limit definition. What is f of x plus pi, x plus h? F of x plus h, what is that? we are composing this original function, f of x equals 2 cosine x, with the linear function x plus h. So what does that look like? We're just going to have 2 cosine. Instead of x, we're going to replace that with what? With x plus h. Okay? All right. In order for us to be able to execute this limit, to compute what the value of this limit is, we are going to have to make use of some identities. Okay? So let's go ahead and list the identities that we need to execute this proof. So review. These are some things you learned in pre-calc on trig identities. We need about, I think, 3 of them here. Trig identities. All right, the first one that you need to know is the sum and difference identity. Okay, so remember, if you have cosine alpha plus beta, that's going to be equal to cosine alpha cosine beta minus sine alpha sine beta. Okay, and then another one, we also have to make use of some limits. You remember that the limit as h approaches 0 of cosine h minus 1 over h, this limit is equal to 0. And then you also have to remember this other trigonometric limit, which is limit as h approaches 0 of sine h over h. That is equal to 1. Okay, most of the formula sheets, these h's are x's, but it doesn't really matter what the letters are. So we're going to be making use of this trig identity and then this trigonometric limits in carrying out this proof, okay? All right, so let's go ahead and apply this identity to this situation we have right here. What is cosine x plus h? Using the sum identities for cosine, f of x plus h is equal to, let me make sure I have enough space, 2 cosine x cosine h minus, well, since we have the 2 there, we want to distribute it to the other quantity also. So we have minus 2 sine x sine h. Okay? I just distributed this 2 to both of them since I don't have the parentheses. All right, so that's that. Now what we're going to do next is we're going to compute the limit as h approaches 0 of f of x plus h minus f of x, that entire thing divided by h. Okay, so let's see, what is that? That's going to be the limit as h approaches 0. The numerator is f of x plus h minus f of x. So we have 2 cosine x cosine h minus 2 sine x sine h. Okay, that minus f of x, which is 2 cosine x. And then we're going to divide that by h. All right, so divide that by h right here. All right, so what we're going to do next, we're going to go ahead and break down this expression into a situation where we can apply these two limits that we already knew before, okay? So what we're going to do, I'm going to move this cosine x piece over. This cosine, I'm going to move it over right here. Let's go ahead and do that. And then I'll leave the sine x over x alone, okay? So this limit now becomes the limit as h approaches 0 of 2 cosine x cosine h minus 2 cosine x, that divided by h. All right, and then minus 2 sine x sine h over h. All right, taking the limit of this entire expression right here. All right, now we're going to use the properties of limits to break down this limit. At the same time, we're going to do some factorization too. So we're going to have the limit as h approaches 0, and the numerator I can factor out 2 cosine x, okay? limit as h approaches 0 of 2 cosine x times cosine h minus 1, all right, divided by h minus the limit as h approaches 0 of sine 2 sine x. Let's write that again. Limit as h approaches 0 of 2 sine x sine h over h. Okay? Now, let's go ahead and do more factorization. Now, one thing you want to note is that cosine x is independent of this limit. What's moving here with this limit is h, so only terms with h's attached to them are going to be impacted by this limit, all right? So I can rewrite this as 2 cosine x, since cosine x, this function is independent of this limit, of, I'm going to change this into blue, okay, of the limit as h approaches 0 of, what do you have left here? Cosine h minus 1 over h. All right, so that minus the same story here. 2 sine x is independent of this limit, so we can pull it out to sine x, and then we are going to be left with the limit as h approaches 0 of sine h over h. Okay? Now, in order for us to finish this limit, we're going to think back to our limit of trigonometric functions. These two right here, we're going to implement them in this situation, all right? So let's go ahead and do that. This limit is going to go to 0, and this is going to go to 1, all right? Both of them, we know that result because of the squeeze or sandwich theorem. If you want to review that, you can go to math.survey.com and get access to the rigorous derivation of the sandwich or squeeze theorem, and also how this can be derived based on the existence of this result right here, on this becoming 1, approaching 1. All right, so let's go ahead and do that. We're going to have, this is now going to become 2 cosine x. This is going to be 0 minus 2 sine x, and then this limit here is 1. So 0 times 2 cosine x is 0. So we're going to have the limit, which is f prime of x, is going to be equal to negative 2 sine x. Okay? All right, we're done with step 1. Step 2, step 2, we're going to find the derivative at a specific x value, namely x equals pi over 2. Okay? So for step 2, we're going to find f prime of pi over 2. So that just simply means we're inputting pi over 2 into this derivative function. All right, so we have negative 2 sine pi over 2. Okay, so what is sine pi over 2? You can sketch your sine function. Sketch a sine function. You remember how it looks like. So you have it going like that to pi, and then from there, went off a little bit. So that goes to pi, and then this to 2 pi. Okay, so right here is pi over 2. So sine of pi over 2 is clearly 1. So this is going to be 1. So we're going to have negative 2 times 1, which is negative 2. Okay, so that's exactly what we were asked to find. We were asked to find the slope of the tangent line. Okay, so let's write down what are the significance of our results in a complete sentence. So this means that the slope of the tangent line to the function 2 cosine x at x equals pi over 2 is negative 2. Okay? All right, now we have to use another method. We have to use the differentiation rules method, which is much faster. Okay, so we're going to do method 2. Method 2 is the differentiation rules. Okay? All right, so we're still going to do steps 1 and 2. Find the derivative first, and then evaluate it at x equals pi over 2, okay? So we know that f of x is equal to 2 cosine x. And then what's the rule? Okay, what rule are we using? The rule is as follows. If f of x is equal to cosine x, then the derivative f prime of x is what? The derivative is going to be negative sine x. Alright, so that's the rule for differentiating cosine function. The derivative of cosine is negative sine. Okay, so let's go ahead and apply it here. F prime of x is going to be the derivative of 2 cosine x, 2 cosine x prime. Alright, we can always factor out the constant using the constant multiple rule of derivatives. So factor out 2 times cosine x prime. So what is the derivative of cosine? Using our rule, we know that it's negative sine. So 2 times negative sine x. And then multiply it out, you have negative 2 sine x. How's your derivative? Okay, so you see the power of the differentiation rules, right? So if, you don't have to do all that limit stuff if you're not asked to do it. You just use your differentiation rules. But the fact that we got the same derivative here and here, where is it? Right here, shows that our answer is in fact correct, okay? All right, now we just did part 1, which is to find f prime. And then part 2, we want to find the slope of the tangent line at a particular point. This is the slope of the tangent line at any x value, okay? So let's fix it. F prime of pi over 2, like we did before, is going to be negative 2 sine pi over 2. And we already know what sine pi over 2 is. It's 1, so it's just negative 2 times 1, which is equal to negative 2. Okay, so I'm just showing you 2 different ways of carrying out the same procedure. So there goes the slope of the tangent line. Okay, now let's move on to the second part of the question. We're asked to write the equation of the tangent line. Okay, so that's part 3, write the equation of the tangent line. Okay, so for the equation of the tangent line, let's write down what we're looking for, equation of tangent line. We're going to have to make use of a formula. Okay, so equation of the tangent line, we're going to use the formula L of x. I'm going to call L of x my tangent function. Okay, that equals f of a plus f prime of a times x minus a. Okay, this is just an advanced variation of the formula you already learned in Algebra 1, which is y equals y1 plus mx minus x1. Alright, so they mean the same thing, okay? But this is a much more advanced notation. L of x equals f of a plus f prime of a times x minus a. So in order for us to write down the equation of a line in algebra, we needed a point and a slope. Okay, we needed x1, y1, and m. Okay, we needed this, and that. So with the formula we're using today, this much more advanced calculus-based formula, we need to find f of a, which is y1. We need f prime of a, which is the slope or the derivative at x equals a, and we also need a. Okay? So you need to get used to using this formula. It's much more powerful than the old formula you knew before. Okay, so let's go ahead and list the pieces that will help us generate the equation of the line. Let's start with a. A is equal to the x value that's at the point of tangency, which is pi over 2. And then f of a is the y value. So we just basically evaluate the function when x is equal to pi over 2. Okay. We know that our function is 2 cosine x, so we're looking for 2 cosine pi over 2. Okay, so what is cosine pi over 2? Let's look at our cosine function again real quick. Just sketch that. Cosine pi over 2, we know that cosine starts from starts from 2, drops down to pi over 2, and then to pi, 3 pi over 2, and then up to 2 pi, like that. Okay, so there goes your your cosine function. Mine's kind of looking weird, but let's try again. So something like this. You learned this in trig and pre-calc. All right, so you can clearly see that cosine pi over 2 is 0. So we're going to have 2 times 0, which is equal to 0. All right, we have our a and f of a, also known as x1 and y1. F prime of a is the derivative of x equals a. A is pi over 2, so we're looking for the derivative at pi over 2, or the slope of the tangent line at pi over 2. We already calculated that earlier in part 2 of the problem, and that's negative 2. So f prime of a is negative 2. All right, so we're going to put all this together to generate the equation of our tangent line. So the equation of our tangent line, L of x, is equal to f of a. Let's write it again so we don't make mistakes. F of a plus f prime of a times x minus a, okay? So let's go ahead and look for the equation of our tangent line in this situation, which is going to be f of a is what? What is f of a? 0 plus f prime of a is negative 2. Negative 2 times x minus a, which is pi over 2. Okay? So let's write this in slope-intercept form. So it's going to be the L of x equals, distribute negative 2x, and when you distribute negative 2 to negative pi, it becomes positive pi. Okay? So this is the equation of the tangent line. All right, we can use our calculator to come up with this exact result. We are also instructed in part, let me just go back to see what the question says. We're asked to plot the graph and sketch and label. Okay, plot with our graphing calculator, then sketch and label. Okay, let's go ahead. I'm going to be using the TI-89 titanium. Pretty powerful calculator for calculus. So let's go to the graphing window. We're going to input 2 cosine x, 2 cosine x, enter. That's the function we're graphing. Let's graph it. Okay, let me stop this for a second. I like to use since I'm graphing a trig function, I like to use the trig zoom. All right, so let's zoom. F2 is zoom. Zoom 7 will give us the zoom trig. It looks much better. So zoom 7. Nice, so that's exactly what we like to see. All right, so this is a graph of f. We also want to see what the graph of the tangent line is. And the beauty of the function we're about to use is that not only does it generate the graph of the tangent line at a specified x value, but it also gives you the equation of the tangent line. Okay, that's excellent. So let's go ahead and do that. We're going to go to the math menu, F5. And then we're going to scroll down to option A, I think. Yeah, tangent. Okay, option A. After 9, press enter. The calculator will ask you what x value do you want to compute the tangent at. So we're looking at pi over 2. Let's enter that. Pi over 2. Enter. Boom. Okay, so you see the equation of the tangent line, negative 2 plus 3.14159. The same thing as negative 2 plus pi. Okay, what was our answer? Our answer was negative 2x plus pi. So the calculator basically has confirmed that all our computations are in fact accurate. Okay, so we have that done. Now let's sketch this graph in on our notes. So we know what the tan function, we're going to try and make it look as nice as possible since we're going to be deducing some facts from the result that we generated. Okay, so let's draw our cosine function. So the maximum displacement, the amplitude is 2. So let's not make it too high so it's not hard to draw. So this is 2, and then that's negative 2. So we're going to be oscillating between these two values. Let's call this pi over 2, pi, 3 pi over 2, 2 pi. We don't need to draw too much because we're focusing on what's happening around pi over 2, okay? So you have a point here, and a point here, and a point here, point here, and then a point here. Okay, so let's go ahead and sketch it. Like that. Do that again. So you sketch it like that. Okay, this is your cosine function. Doesn't look too good, but you guys know it's just a sketch. Alright, so there goes my sketch. Doesn't look too nice, but let's look at a calculator. Alright, so there goes a tangent line right there, so we can sketch it to the best of our ability. The tangent line is going to look something like this. It's tangent at that point right there. Alright, so let's go ahead and label what we have. So this is the function. Let's make that green, f of x equals 2 cosine x. And then this is the tangent line. We chose to call it L of x. We don't want to call it f of x so we don't get confused, okay? So the tangent function is negative 2x plus pi. Okay, let me go ahead and show you a visualization as to what's happening. Okay, so this is a cosine function, 2 cosine x. What we're going to be doing is I'm going to be showing you a visualization as to how the slope of the tangent line basically changes as you take a look at the behavior of the tangent line at different values of x on this function. So this is just a piece of the 2 cosine x function, okay? Remember that pi over 2 is basically, if you do it in your calculator, let's calculate that real quick. What is pi over 2? Because this program we're using does everything using decimals, okay? So pi over 2 in decimal form is 1.57. So somewhere here will be, basically here will be where we're looking at, okay? All right, so let's look at the tangent line. So this is a tangent line at a particular x value, okay? We notice that it's positive 0.82. Now let's slide it. So what you're looking at is how the value of the tangent line changes at different values of x, okay? It's positive, drops to 0, becomes negative, and then it changes, all right? So what we're looking for is the equation of the tangent line. Let me stop it when x is pi over 2. Okay, we know when x is pi over 2, the cosine function intersects the x-axis, right? So somewhere there. Let's make it perfect. Somewhere there. I can't get it too perfect. Okay, anyway, somewhere there. You see what the computed slope is? The slope is negative 2. So this line right here, that's what we're looking for. We're looking for the equation of this line. Okay? Note that the slope of this tangent line changes for different x values, but we want to fix it to x equals pi over 2, which is right here. F of x is supposed to be 0, but it's just not computed it properly. So at this point right here, you see that the slope is negative 2. Okay, so that just basically shows that our answer is correct. And hopefully this visualization helps you understand what we're talking about when we're looking for the slope of the tangent line at different points. Okay? All right, so now let's go ahead and write down some facts about what we've been able to come up with. All right, so for the last part, we are supposed to write down everything we can deduce from this situation right here. So let's go ahead and do it. So first thing I can deduce from this situation, number 1, is that the instantaneous rate of change, rate of change, I'm going to call it IROC. Okay, the instantaneous rate of change of the function f of x at x equals pi over 2 is what? The instantaneous rate of change is negative 2. Why? Because the instantaneous rate of change, the IROC at x equals pi over 2, is the same thing as the derivative at pi over 2. They mean the same thing. Okay, this is IROC right here. Instantaneous rate of change at a particular x value is the same thing as the derivative. Okay, keep that in mind. What else can I deduce from this situation right here? Number 2, I can deduce that the function is decreasing at x equals pi over 2? Well, it's obvious from the graph, but what does calculus tell us about that? Can we use our tools from calculus to support this conclusion? Absolutely. The function is decreasing at x equals pi over 2 because the derivative at that point is what? The derivative at pi over 2 is negative. So if you have a negative derivative, that basically means that the slope of the tangent line is negative, so your function should be decreasing at that value. Okay? All right, number 3, what can this line help us to do? Well, this tangent line, let's rewrite it, L of x equals negative 2x plus pi. Let's go ahead and write it. The tangent line, L of x, which is equal to negative 2x plus pi, can be used to estimate or approximate the function. Okay, it can be used to approximate f of x near that point of tangency near x equals pi over 2. So the closer you get to pi over 2 from both sides, the much more accurate your approximation will be. Okay, and if you notice, if you really zoom into this point right here, you notice that the tangent line and the function are exactly the same. All right, so what does that mean? Well, let's say we wanted to approximate something really, really close to pi over 2. So let's say we wanted to find f of pi over 2, give or take 0.0001. Okay, so plus 0.001 would be to the right, and then minus 0.001 will be to the left, of course. So this output can be approximated using the tangent line. Can be approximated by evaluating the tangent line at that value, pi over 2, give or take 0.0001. The farther you go from the point of tangency, the more inaccurate your approximations are. Okay, you can see how it's getting wider and wider the farther you go away from the specified x value. Okay? All right, so that's one powerful application of the tangent line. It can be used as a surrogate to the actual function. All right, lastly, how is the estimation though? How is the approximation? Is it an over approximation, an overestimate, or an under approximation, or an underestimate? If you take a look at the tangent line and the function, you notice that if you're to the left of the function, if you're to the left of the point of tangency, the tangent line is above, right? And then if you're to the right, the tangent line is below the function. So that basically tells you that if you're to the left, you're going to have an overestimate, okay, because the tangent line is above. And then if you're to the right of this point of tangency, you're going to have an underestimate. It's going to be smaller than the actual value. Okay, so let's write that down in the last piece. Question number 4, L of x is an under approximation. An approximation of f of x when x is greater than the point of tangency. All right, x is greater than pi over 2. Why? Because the tangent line is above the function. Okay, is above the function. That's one way to say it. Or the function is concave up. Okay, or the function opens upwards, or f of x opens upwards. So if a function opens upwards, the tangent line must reside underneath. Okay, so no matter how you think of it, if it opens up, the tangent line will always be underneath the function. Okay, and then how about to the right, to the left of pi over 2? L of x, the tangent line, is an overestimate. Over approximation, we can also call it overestimation, is an overestimate of the function of f of x when x is less than pi over 2. Okay, why is it an why is it an overestimation? Is because the tangent line is below. Okay, the tangent line is below f of x, or f of x opens where? Or f of x opens up, opens up, I'm sorry, opens downward. Okay, opens downward. So if the function opens downwards, all the tangent lines are going to be above it. Okay, it's going to be above. The estimation of the tangent line will be above that point of tangency. So that's the fourth conclusion that we can draw from this situation. So I'd like to thank you so much for taking the time to watch this presentation. Do feel free to subscribe to our channel for updates to other cool tutorials such as this. And do post a comment in our comment section to let us know what you think about this tutorial or to make requests for other AP Calc lessons. More clips can be found on math.serve.com as indicated earlier. Thanks again for watching and have a wonderful day.